our guest speaker, Amory Lovins, be our speaker and presenter today on disruptive energy futures. But before we get to that, we have a little business to do. One thing is, please, if you have any questions, they'll be answered at the end of the presentation. And so if you have questions, please enter them into the chat. Another thing is that we are recording this meeting, and the recording will be available on the NTREG website after the meeting. And the other thing is welcome, and we look forward to Amory's presentation. So what I'd like to be able to do is go into our meeting section. We'd like to do this in a short period of time. And so I would like to have Lissa Magel, who is our membership chairman, give us a quick report.
Hi, everybody. This is Lissa Magel. As Michael said, I'm the membership coordinator for NTREG. We're the North Texas Renewable Energy Group, which we're the local chapter or the North Texas chapter of the Texas Solar Energy Society. And I want to welcome everybody today. Apologize for anybody who logged in a little bit early, because Zoom is a great invention, and it's allowing us to have a speaker from afar like Amory Lovins, but it also means we forget about things like time zones. So sorry we didn't put Central Daylight Time on the time for the meeting, but our meetings are always free and open to the public. But that being said, having things like Zoom and these remote meetings does cost a little bit of money. To join NTREG as an individual member is only $20 a year. So we very much welcome memberships, but we also understand that that doesn't work for everybody. So we welcome anybody who just wants to attend. We do have business level memberships and professional level memberships for people who are in business for themselves. But I will again welcome everybody, and I'll turn it back over to Michael. But if anybody has any questions about membership, you can send me a little message in the chat here. If you have questions about your current membership status, I can look you up online if you send me a message in the chat. And thanks again.
Yeah, thank you, Lissa. Next, I'd like to present Mark Whitty, who is our events chairman, and talk a little bit about events. Mark?
Good morning, everyone. This is Mark Whitty, and we appreciate everyone's participation in our meeting today. With respect to the events update, the Solar 101 presentation update is complete, and so it's ready to go. Our goal for NTREG is to make one presentation or more every month to an outside group. So with the presentation ready to go, it's really up to all of us to find groups that are interested in having a very informative and interesting presentation made to their group. And it can be any kind of group, educational, religious, it doesn't matter. So any groups that anyone may be aware of that would be interested in a presentation, please let me know, and we will arrange to make a presentation. The other update is with respect to the solar tour. It's an annual event. It's actually part of the American Solar Energy Society nationwide tour, and we're part of it. We've been part of it for many years, and we're currently in the planning stage, and we will have an update on that a little bit further along in this year. The solar tour is scheduled for October 2nd, so just put that on your calendars and be prepared to receive other updates in the future. Thank you.
Mark, do you mind mentioning something about the Austin Cool House Tour?
The what? Pardon me, Mike?
The Austin Cool House Tour.
Oh, yes, thank you. The Austin Cool House Tour once again, that's an annual event that's really put on by the Texas Solar Energy Society. It's scheduled for tomorrow. It's virtual. Anyone that wants to attend can go register. It's free. And just go to the Texas Solar Energy Society webpage and register, and they'll send you the link for the virtual meeting. But thank you for reminding me, Michael.
Yeah, what time, do you recall what time that is occurring? Is it 11 to 2 or something?
I think it's 10 to 2.
10
It
to
might
2.
be 11 to 2, but I think it's 10 to 2. They're going to record it, so even if you can't make it during that time frame, if you register, you can view the Tool House tour at your leisure whenever you have the time.
Okay, I'd like to make a special little report regarding special projects that we're working with the city of Dallas on, and that is the Dallas CIC CCAP program. We're doing an evaluation. We're preparing a rubric questionnaire for city buildings, primarily right now, libraries and community centers, to their ability to become a resiliency hub. And so we've had several meetings and we're moving forward on that. So we'll keep you all posted on how that results. Anyway, moving forward, do we have any announcements from members? I throw that back out.
I'm trying to get unmuted. Michael, just real quick, 2 things. For those of you who don't know me, I am with the City of Dallas CCAP program. We've been asked to develop some specifications to include into the 2022 bond program to ensure that the CCAP measures are appropriately included into those pending facility projects. And so I may be reaching out to you either to proof what I've got or for some ideas. The other thing is that we got our environmental commission approved by council the end of April. At this point, we are trolling for people who live in the city of Dallas who might have an interest in serving on that as a commission member, and or if you do not live in the city of Dallas, we are also looking for people to assist with a technical panel so that we can get both the neighborhood perspective and the technical background on some of the things in the CCAP. So if there is anyone that has an interest, I will put my email in the chat. Feel free to reach out. Thank you.
Thank you, Sue. Are there any other comments or notices from the members? Any guests have any comments they want to make? We always refer to our Climate Reality Project Association. I want to just bring to everyone's attention that they have a virtual meeting monthly on the 3rd Saturday, 1 to 3 p.m. So you should, their website, we can post that in the chat if you're interested in joining them for their monthly meetings. Are there any other guests or members that would like to make an announcement before we move forward? If not, I'm going to turn it over to Paul Westbrook, who is a member, and we're thankful that he is bringing Amory Lovins to us for his presentation on disruptive energy futures. So, Paul, it's all yours.
Thanks, Michael. So how do you introduce somebody that everybody probably already knows is always a challenge, right? You can go read about awards and stuff on the web, but I thought I'd make it a little more of a personal introduction. I first became aware of Amory probably in the late 70s or early 80s when I read somewhere his 1976 essay, Energy Strategy, The Road Not Taken. And it was talked about the soft energy path of efficiency and renewables and you know, how being different from our hard energy path of military to defend oil and everything else. So it really had an effect on me, even in the early days. He formed the Rocky Mountain Institute back in 1982. And I believe it was about 1985, he coined one of my favorite terms you may be familiar with, the negawatt, which is the energy you don't use. And I think the story I've heard, it was born from a typographical error in a Colorado Public Utilities report where they mistyped megawatt since the M and N are right next to each other. Now, where I met Amory was back in 2000, there was a group called Sustainable Dallas that had a conference, and they had flown Amory in to speak at this conference. And when he landed at the airport, he had become interested in semiconductor plants, and he asked the person who picked him up if she happened to know anyone who worked at Texas Instruments. My phone rang because the person that picked him up was the wife of my home builder from 4 years earlier. And about 30 minutes later, we were sitting in a conference room at TI, hatching the plan for what became the most efficient semiconductor fab in the world, right there in Richardson, our fab. So the final thing I think I'll say is, since he wrote it back in 2008, I've kept a copy of his Applied Hope letter, kept it on my office wall at work, and I would refer to it often when I would get a little dejected about we weren't moving as fast as I would like. So I'm just going to read a tiny clip from that. The most solid foundation we know for feeling better about the future is to improve it tangibly, durably, reproducibly, and scalably. Hope becomes possible, practical, even profitable when advanced resource efficiency turns scarcity into abundance. So for a big vaccination of applied hope, please welcome Amory Lovins.
I believe someone has to unmute.
Okay, I'm now unmuted. Can you hear me?
We can hear you.
We're all saying yes, but we're muted.
Okay, and can you see a big blue Rocky Mountain Institute logo?
Amory, it's working fine. This is Dan.
Okay, we're off and running. And want to thank you all for the honor of reporting some energy and electricity surprises that may help you, I hope, in North Texas by putting your good work into a global context. I'm going to take General Eisenhower's wise advice to make tough problems soluble by expanding their boundaries to encompass more options, more synergies, to include everything the solution requires. All four energy using sectors, transportation, buildings, industry, and electricity, save more energy faster together than they do separately. And all four kinds of innovation, not just technology, but also design, not only public policy, but also new business strategy, can combine to create deeply disruptive game changers while the old industries are still putting on their boots. Ford's auto industry, Edison's electricity industry, and Rockefeller's oil industry changed the world. And if Ford and Edison took a very long nap on one of their car camping holidays together, and they woke up and saw their businesses today, they would recognize almost everything except the electronics. Yet their industries now face vast disruption as 21st century technology and speed collide head on with 20th and even 19th century institutions, rules, and cultures. And now the first two of these three great industries, autos and electricity, are coming together to eat the third one, oil and then gas. And as we might imagine, Ford mischievously muttering to Edison, let's see what happens when electricity displaces gasoline. Then those electric cars add flexibility and cheap distributed storage to the grid and make batteries actually cheap for everybody, helping the grid to integrate variable solar and wind power so that distributed renewables can displace giant thermal power plants and their fossil fuels. Let's start, as we always should, with efficient use. Saved energy is already the world's biggest energy source, bigger than oil. Just the energy saved worldwide since 1990, about 2/3 of it by smarter technologies, now supports more energy services than oil or any other source does. And if the United States total primary energy demand had kept growing in lockstep with GDP since 1975, Americans would have used this much energy. Instead, we cut that use by more than half, saving cumulative energy equivalent to about 28 years of current use. Meanwhile, the renewable energy output doubled, very impressive, yet with 27 times less cumulative impact than the savings. Renewables get virtually all the headlines because they're visible on the skyline or the rooftop, but energy is invisible. The energy you don't use is almost unimaginable. And yet, from 2010 to 2016 in the world, saved energy avoided 3 times as much CO2 emission as all the renewable and nuclear growth did. Another bit of history, around 1975, our government and industry all said that primary energy productivity, the GDP produced per unit of primary energy used, could never go up. A year later, I heretically suggested it could rise 257% in 50 years. So far, it's risen 152% in 45 years. And yet, just the innovations already added by 2010 can raise energy productivity by another third, twice what I originally thought, and add a third the real cost. And today that's looking conservative because optimizing buildings, vehicles, and factories as whole systems, not as piles of parts, can often make very big energy savings cost less than small or no savings, turning diminishing returns into increasing returns. This paper, free online, just search on the title, with a fun 4-minute video abstract, explains why making energy savings several-fold bigger can actually cost less, because it uses not more but fewer devices, not fancier but simpler devices, more artfully chosen, combined, timed, and sequenced. Ore reservoirs and metal ore bodies are finite and depletable assemblages of atoms, but energy efficiency resources are infinitely expandable assemblages of ideas, depleting only stupidity, a very abundant resource. A few examples. My wife Judy and I live 2,200 meters up, 7,100 feet in the Rocky Mountains in Old Snowmass near Aspen, Colorado, where temperatures used to dip as low as minus 44 C, minus 47.5. And we've seen as much as 39 days of continuous midwinter cloud. It was snowing last week. We had frost a couple of weeks ago. Our house does no combustion, though that's so 20th century. Super insulation, ventilation, heat recovery, big super windows insulating like 16 or even 22 sheets of glass, but looking like 2, costing less than 3. Make the building 99% passive solar heated, 1% active solar. And super efficiency added less construction cost than eliminating the heating system subtracted. In other words, we bought enough efficiency to get rid of the heating system, and then we paid for that efficiency by not needing the heating system. So it was paid for right up front with some money left over. We ended up saving 99% of the space and water heating energy, about 90% of the household electricity, for which the bill was $5 a month when we first moved in at a 7-cent rate. We saved half the water. All those together paid back in 10 months with 1983 technologies. Today's are a lot better and cheaper. The house wraps around the central atrium seen here in a February snowstorm. And so far we've produced 78 passive solar banana crops. Somebody said I had really big earphones. And the house inspired several 100,000 European passive buildings, which likewise have no heating and roughly normal construction cost. And wherever you live, integrative design gives you lots of benefits from each expenditure. So the white arch in the top of the upper middle photo has 12 different functions, but it has only one cost. It works anywhere. Soon after we moved in, an architect from Thailand, Professor Suthon Punyatakaran, visited our house, and he decided to adapt his integrative or our integrative design approach to his own 350 square meter house he was building near Bangkok. And he ended up saving 84% of the air conditioning capacity, 90% of the air conditioning energy, with normal construction cost and better comfort. And nearly everybody in the world lives in a climate somewhere between his and mine. What about a hot, dry climate? Well, a quarter century ago, this 155 square meter experimental house achieved superior comfort up to at least 46 C with no air conditioner. The designers improved the layout, optimized the window location, adopted an oriented strand board wall that saved 3/4 of the wood, doubled the insulating value, improved the strength and air tightness, durability, stability, construction speed, and cost $2,000 less to build. And these improvements cut the site energy to 15% below the strict California standard and saved $4,000 of construction cost. Then better lights, appliances, glazings, and hot water system were justified by energy savings totaling 60% and eliminating the furnace. Then the remaining one of the original 3.5 tons of space cooling and $1,500 of construction cost were eliminated by further improvements that cut the cooling load, even though they were not justified by energy savings. So altogether, by this point, we got the mature market construction cost to about $1,800 below normal for an 82% energy saving below the strictest code in the country. And the present valued maintenance cost was about $1,600 below normal. The energy savings for space and water heating, space cooling, refrigeration, and lighting were 80%. And in heat storms, neighbors were taking refuge in this house with no air conditioner when their own 5-ton units couldn't cope. You'll find details of this in my ASHRAE Journal Centenary talk in 1995. Now, we used integrative design in 2010 to retrofit the Empire State Building, saving 38%, later 43% of its energy use with a 3-year payback. More on that in a minute. And then 3 years later, our cost-effective Denver retrofit of a federal complex saved 70%, making this half-century-old structure more efficient than what was then the best new U.S. office at NREL, which in turn is only a third as efficient as RMI's passive net positive no mechanicals innovation center in Basalt, Colorado. And now there's a Bavarian building using 2/5 less energy than that. But all these technologies existed over a decade ago. What mainly improved is not so much technology as design. How did our retrofit save 2/5 of the Empire State Building's energy? Well, we started by remanufacturing its 6,514 windows in a temporary window factory set up on a vacant floor, making them into super windows that pass light through but block heat. And that, plus better lights and office equipment and air handlers and so on, cut the maximum cooling load by 1/3. But then renovating smaller chillers instead of adding bigger chillers saved $17 million in capital cost, paying for most of those improvements and cutting the payback to 3 years, or under 1 year if we had counted non-energy benefits to the owner or the tenants. A big energy service company using disintegrated design offered the same 3-year payback, but with only 1/6 the savings we got. So they didn't get the job. Now the owner is going back with even better integrated design to save another 40+%. Of the 20 most efficient commercial buildings in North America, RMI's Basalt office is the most efficient in the 2 coldest climate zones, keeps people cool by 11 and warm by 10 passive methods, including hyperchairs, built-in 3.6 watts of silent fans and 14 watts of electric car seat heaters can ensure ASHRAE comfort as the room, if the room is anywhere from 18 to 30 C, 64 to 86 F, although in fact it's kept within a degree or two of 21C70F. If we actually use those hyperchairs, we would further reduce the building's energy use intensity of 11.4 thousand BTU per square foot year, or 36 kilowatt hours per square meter in year. My favorite part of the building is the 25 square meter nega mechanicals room, where I want to sneak in some night with a roll of yellow industrial tape and mark on the floor like bodies at a crime scene where the boilers and chillers and stuff were supposed to go before we designed them all out and took the space back. We expect this building's cost premium, mostly soft costs, to drop to about zero with wider experience, just as Germany's best passive buildings have done. More broadly, to keep people comfortable in hot places, you first cool the people, not the building. So here's one of those hyper chairs. The building has no comfort sensation, cool the people. And then you expand the range of conditions in which people feel comfortable. For example, good ceiling fans expand your summer comfort range by 5 to 7 Celsius degrees. Then you minimize unwanted heat and humidity gains within or into the space. You consider an active, sensible heat exchanger and a passive latent heat exchanger. Next, you apply passive cooling, then active but non-refrigerative cooling. And next would come super efficient refrigerative cooling. And like Liang Locke's triple to quintupled efficiency, but cheaper HVAC in Singapore. And then, next after that, if you needed it, would be cool storage and controls. But actually, we need never get as far down the list as refrigerative cooling to save 90 to 100% of the cooling energy with better comfort and uptime and lower whole system capital cost, even in the most severe climates. Unfortunately, most practitioners take these options in reverse order, worst buys first. Now, what about tropical climates, say Houston, Corpus? Well, 6 weeks ago, our India-based Global Cooling Prize announced the winners of a contest to cut affordable window air conditioners' climate impact by at least 5x. And both winners raised energy efficiency over 5x, as it turned out. Both of them are large manufacturers that between them have a quarter of the world market in window air conditioners, and they're coming to market with this. But better buildings can first displace that cooling equipment. So here's a sketch of mid-rise apartments that proved popular in Mumbai's monsoon with Houston-like design conditions. They use passive, convectively vented double walls and super efficient ceiling fans to keep you feeling about 16 to 19 Celsius degrees cooler at just 2% higher construction costs. And with a few further refinements, they could deliver decent comfort with no air conditioning. Also in muggy India, Rohan Parikh's team built 1.5 million square meters of offices using 80% less energy and with 10 or 20% less construction costs than Indian norms, and yet with superior comfort and satisfaction. Glare-free lighting, like you see on that big floor plate on the right, is delivered throughout by contract. If people gripe about glare and demand blinds, the architect doesn't get paid. And by the way, on the left photo, if it looks to you like the building's flipped upside down, yes, that's what they did, because they paid less for the extra structure than they saved up front on HVAC by self-shading. Pretty cute. In Europe, industrializing mass retrofits to net zero energy and streamlining their finance and soft costs is now getting cheap enough to finance entirely from saved energy while extending building life and improving amenity, health, and value. This whole retrofit has even been demonstrated to be installable in a single day while you're off at work. And now similar methods are expected to cut energy costs 80% in 9 old Brooklyn apartment buildings. RMI's realized collaboration with DOE and California Energy Commission is adapting them to the United States. Whatever exists is possible. IPCC reported 7 years ago that among new European buildings on the left and retrofits on the right, with bigger savings in both cases towards the right, The best projects, the ones down along the horizontal axis, saved up to at least 90% of their energy without costing more per unit of saved energy. Many projects actually cost far more, you see that big vertical scatter, by not adopting the best practices shown, and the difference is a business opportunity. And about a decade after those buildings, new techniques are emerging. For example, purely radiative cooling can keep people comfortable outdoors in humid Singapore at upwards of 32 degrees C without moving, drying, or cooling the air. Instead, in this shaded but open-ended 10 square meter pavilion, kind of like a bus stop shelter, this experiment cooled people just by absorbing far infrared radiation from their bodies into vertical panels cooled by surface tubes circulating slightly cooled water. And to prevent heating by and condensation from the ambient air, the front of the panel is shielded by an air gap 50 micron polyethylene film that's transparent to 82% of the infrared that your body radiates. As the extended psychrometric chart shows, they had to extend it because nobody had tested this regime before. Mean radiant temperatures around 23 to 25 C, 73 to 77 F, can deliver comfort up to at least 32 C or 90 F at 80% relative humidity. Such mild cooling, just the 5 to 7 C subambient to feed the panel, can be done passively with no electricity by special surfaces that radiate infrared into the sky, and therefore sitting in direct sun, they feel cool to the touch. And I have a paper in peer review at Proceedings of the National Academy of Sciences where the work you're looking at here was reported, called Hot Cars, Cool Bodies, No Air Conditioner, suggesting we do the same thing in our cars and save about $7 billion a year in the US alone. What about home appliances? Well, this Swiss fist-sized heat pump can deliver 6 to 15 units of hot water per unit of electricity. It's a little over 60% of Carnot efficiency limits. This dramatically more efficient and safe and otherwise superior Swiss electric cooking system uses vacuum insulated pots to cook with about 2.5 to 4 odd times less electricity than induction cooktops. And the highest leverage for fair development comes from efficiency gains that make electricity affordable to the poor. In this 27 watt electric household, Berkeley Lab uses solar panels a third smaller than what's shown in the picture to power 7,000 lux of LED lights, a mobile phone charger, a clock radio, a table fan, and a 56 centimeter color television. Of course, the technologies keep improving. The latest biomimetic fan can move a well-collimated beam of air at 650 CFM with just 6.2 watts. So it's better than the one shown there. Super high efficiencies cut total capital cost of the system by half, empowering twice as many off-grid families for the same investment and enabling cheap and highly reliable DC solar microgrids with the PV, the batteries, and the appliances all running on the same low voltage DC with no inverters. And it turns out this eliminates so many back and forth AC/DC conversions, losing water to each time, that it nearly doubles the practical system efficiency. So that work by Junjun Walla just got the IEEE Global Award a few years ago. And if you invest to make things that save electricity like these appliances, rather than supplying more electricity, you're going to need about 1,000 times less capital, and you'll get it back in about 10 times faster. Then lower intensity and faster velocity of capital multiply. So you end up needing about 10,000 times less capital for the most capital intensive sector, electricity, which devours about 1/4 of global development capital. Freeing up that capital to fund other development needs is the biggest macroeconomic lever we know for global development. Just buy negawatts whenever they're cheaper than megawatts and reward providers for cutting customers' bills, not for selling more energy. Unfortunately, Texas doesn't yet do either of those things. Now, industry uses half the world's energy and electricity predominantly to make stuff. But smarter structural design can profitably save at least half the world's cement and steel that now release 15% of global CO2. For example, substituting tension for compression structures typically gives better strength, aesthetics, and cost with 1/8 the tons. Fabric forms can save over half the concrete in many shapes by putting strength and stiffness only where they're needed. And then the mass savings compound because you need less strength to hold up less weight. This 4 or 5 centimeter thick folded concrete slab replaces a 30 centimeter steel and concrete slab. And it can also help fit 3 stories with unchanged ceiling height into the vertical space normally needed for 2 stories. Then an airy 3D printed bridge with that dendritic structure can replace massive concrete structures that mostly support their own weight, but this bridge can mainly hold up its payload. This beautiful stainless steel bridge, by the way, was 3D printed. And then producing the remaining cement and steel using green hydrogen and other materials can adopt not just cleaner, but also super efficient processes and equipment. For example, RMI's latest $50+ billion worth of industrial redesigns typically found 30 to 60% energy savings on retrofit, paying back in a few years, and far performing the brown zone in the upper left, where most energy service companies deliver disintegrated design. Our new build projects generally found 40 to 90+% savings with lower than normal capital costs. And here's one of those data points for Paul, whom we helped with the redesign of TI's new semiconductor wafer fab to use 40% less energy with 30% or $230 million lower construction costs. So it got built in Richardson, not in China. Its system efficiencies eliminated one of the 2 utility floors, and as of 2017, it had inspired cutting company-wide chip-making energy intensity by 62%, water intensity 56%, greenhouse gas intensity 57%. RMI's next wafer fab design, by the way, showed how to save about 2/3 of the plant's energy and half its capital costs while replacing all 22,000 tons of chillers with any of 3 natural cooling methods that can yield upwards of 100 units of cooling per unit of electricity. Now, to see how, let's start with pumping, the biggest use of motors. If the roughly 100,000 kilometers of fractal blood vessels in your body down to the teeniest capillaries had the design and the friction of standard industrial piping, you would need a heart bigger than your body. Very inconvenient. But in fact, your 1/3 of a kilogram, 1.5 watt heart suffices because your blood follows nature's standard design, laminar vortex flow, with 1/10 the friction of normal industrial piping. Just better pipe and duct design, saving about 80 to 90% of the friction, actually 97% in my house, and therefore of the pump and fan power, could, if fully deployed, save roughly half the world's coal-fired electricity, with paybacks typically under a year in retrofit and instant in new build. But this isn't yet in any standard engineering textbook, industry forecast, government study, or climate model. Why not? Because it's not a technology. It's a design method. And most people don't yet think of design as a scaling vector, a way to make things big fast. To wring out friction, we simply use big pipes and small pumps, not small pipes and big pumps. And to eliminate elbows in their friction, we lay out the pipes first, then the equipment, laying out supply pipes as if they were drains. Notice on the left that blue pump toward the right is so small it kind of looks like a decimal point error, but that's all you need when the pipe gets fat. Notice also that the pump is raised up on a plinth to meet the pipe rather than dipping the pipe down to the floor to meet the pump and then back up again. Thus, our colleague Peter Rumsey's retrofit of the Oakland Museum's condenser water pumping loop cut the pumping energy by 3/4 with a 2 or 3 month payback, and it eliminated 15 pumps that will never again waste energy and maintenance costs. Then he repiped the chilled water loop and added variable frequency drive. That doubled the flow and saved 85% of the energy. Or in big buildings, normally we pipe the cooling tower water back to the chiller's condenser like this. But if we lay it out this way instead, as Peter does, everything gets better. Why don't we all do this? Just force a habit. You know, we should bend minds, not pipes. And what does such savings mean for the 3/5 of global electricity that's used in motors, half of it to run pumps and fans? Well, in a typical pumping system, from the fuel burned at the power plant to the end use, there are so many successive losses compounding that only 1/10 of the energy in the fuel comes out the pipe as flow. But now turn those compounding losses around backwards from right to left. They turn into compounding savings, and every unit of flow or friction you save in the pipe saves 10 units of fuel and cost and emissions and what Amory Lovins calls global weirding back at the power plant. And as you go back upstream, the components get smaller and cheaper, so the total capital cost goes down. And then we can make the drive systems 80 or 90% smaller and at least twice as efficient by a whole system retrofit, using not just the usual 2 improvements, but 35, of which 28 are free byproducts of the first 7. Then you end up saving several fold more energy at about 1/5 the unit cost. Now let's apply this logic to big old data centers. About 2/3 of the fuel fed into the power plant is lost in the plant and a bit in the grid. Then half the metered electricity is lost in the cooling system and uninterruptible power supplies, together about half the total capital cost of the whole facility before it gets to the servers. And then half the server energy doesn't reach the chips because it's lost in inefficient, usually very underloaded power supplies and in zillions of fans to take heat that largely shouldn't be there off the motherboard into the room so we can do dumb things with it. Then the next problem is severe underutilization of computing resources, especially through insufficient virtualization. So the resulting energy flow, that teensy stalk at the lower right corner, is about to disappear. So let's magnify it. Next problem is bloatware, running many inefficient threads and processes, unnecessary ones, making simple tasks very complex because compute cycles were cheaper than programmers' attention and someone else bought the energy. Downstream of all that, you might even have inefficient business processes. So multiply along the bottom scale and you find altogether a few 100,000ths of the original fuel energy is actually delivering customer value. What do we do about that? Where do we start fixing it? Start downstream, start at the end. First, write elegantly terse code, optimally compiled with the goal that every compute cycle is a needed and wanted one. And originally I'd assumed this could save about an order of magnitude in compute cycles. Recent tests suggest it's 2 orders of magnitude. That's how bad the bloatware is. And the shift to mobile devices now makes this very worthwhile to fix because you're stretching battery life. Now, you can then at least quadruple server efficiency, now even more, and the servers will need a lot less cooling and power supply, both of which can be done in smarter ways. We can even save half the utility losses by using fuel cell trigeneration, cheaper than the uninterruptible power supply it displaces. Multiply these savings from downstream to upstream, from right to left, and you get at least 2 orders of magnitude energy savings. Now, this diagram was made up for an actual project with EDS, not yet part of Hewlett Packard at that point in 2009. And the client rejected most of our recommendations. So we were only able to triple efficiency at the same capital cost. But our partner EDS said that had our recommendations that they agreed with all been adopted, we would have saved about 95% of the energy of that data center at about half the total capital cost. Now, even with limited integrative design, RMI rigorously showed a decade ago in a book called Reinventing Fire that US electricity use could shrink 25% by 2050, despite all electric automobiles and a 2.6-fold bigger GDP. So that's quadrupling the efficiency of using electricity, and it turned out to cost a tenth what we now pay for each kilowatt hour. That vast overhang of unbought efficiency holds at risk many power plant and fuel and grid investments. Let me show you 3 slides about electricity demand in the US, where for reasons I explained in the Forbes blog cited at the bottom, we've been saving fuels twice as fast as electricity. But in the 13 years after electricity demand peaked in 2007, but for weather anomalies in 2018, absolute electricity use drifted down 2.3%, while real GDP grew 18%. And that decoupling has been gathering force for a quarter century, as shown by these benchmarks. And Jonathan Kumi has just graphed how normal it really is. You notice in the middle, well, at the left, that US electric use decoupled from economic growth in 1994. Electric intensity has long fallen just as fast in the middle graph as primary energy intensity. And even before the pandemic, most developed and some developing countries were seeing electricity demand slump or reverse. Those that refuse to believe it have been embarrassed. These trends are least visible in Texas because of state policies that favored supply over efficiency. So altogether, America's electricity use, instead of growing 1% a year as officially forecast, could shrink 1% a year despite completely electrified autos. And so far, the actual pattern in orange kind of looks closer to that view than to the current official forecast, 1.5% a year growth to 2050. I suspect those who now forecast a many-fold increase to 2050 electricity use to electrify other sectors are exaggerating future demand and risking building many pre-stranded assets by not competing or comparing efficiency with supply. That's mainly why the much quoted Princeton Net Zero America study assumes 2 to 4 times as much electricity demand as we found in Reinventing Fire, even though we didn't buy nearly enough efficiency. And that high demand in turn largely causes the Princeton Group's impressively granular supply side challenges. What about oil? Well, nearly half of US oil fuels automobiles, so let's start with their physics. Just a fifth of a modern US car's fuel energy reaches the wheels and moves the car. And of that so-called tractive load, nearly half, rising as the cube of speed, is to heat the air that the car pushes aside. Most of the rest is heating the tires and road, and only about the last 6% of the fuel energy accelerates the car and then heats the brakes when you stop. But 19/20ths of the mass you're accelerating is the heavy steel car, not you. So just a 20th of that 6%, or about 0.3% of the fuel energy, ultimately moves the driver. Not very gratifying after 1 1/3 centuries of devoted engineering effort. But both the acceleration and the rolling resistance depend on mass, which therefore causes most of the tractive load. Automakers cut losses mainly in the powertrain where the big losses are. Like asking Willie Sutton, why did you rob banks? He says, because that's where the money is. And that's harder than reducing tractive load and far less rewarding, because saving 1 unit of energy in the powertrain saves only 1 unit of fuel in the tank. But saving 1 unit of energy at the wheels avoids 4 or 5 additional units you don't need to waste getting it to the wheels, and therefore leverages 5 or 6 units of fuel saved at the tank. Therefore, we should first reduce tractive load, then improve the powertrain, which then shrinks for the same acceleration, F equals ma, And that saves more mass, and it also saves capital costs to help pay for the lightweighting. The sequence can indeed make lightweighting approximately free, as BMW showed in the still popular 2013 carbon fiber electric car that I drive. It made money from the first unit off the assembly line in 2013. Its carbon fiber was actually paid for by needing fewer batteries to move less weight. Fewer batteries also recharge faster. Integrative design makes the saved weight snowball far more than other automakers assume. The assembly is radically frugal, eliminates the conventional body shop and paint shop, the two hardest and costliest steps in making a car, and it's much better for the workers. So the quadrupled efficiency you end up with is uncompromised, and it brings many driver benefits. I have an SAE paper documenting all this. It's in the lower right. Now, two hypercars plan to enter the market late this year, both from firms I advised to declare an interest, will change the game again. Most drivers will not need to recharge this two-seat electric three-wheeler because its topside solar cells capture enough energy to drive 40 to 60 kilometers a day. Normal commute. It's as if your present car magically added about 7 liters of fuel to its tank each day you park it outside. To make a long road trip, you can quickly recharge the batteries with household electricity for ranges up to 1,000 miles, 1,600 kilometers. And you can see here how tiny the batteries are because the car is equivalent to 343 miles per gallon. So my BMW and Tesla electric cars are among the most efficient sold, but this carbon fiber and glass fiber two-seater will nearly triple their efficiency to the equivalent of under 0.7 liters per 100 kilometers. And its composite body looks very crash-worthy. The Dutch competitor Lightyear's 5-seat four-wheel 725 kilometer range aerodynamic car has 5 square meters of solar cells, and it's equivalent to 251 miles per gallon equivalent. It can gain 12 kilometers of range for every hour sitting in the sun. So the charging infrastructure others must pay for, these super efficient vehicles aim to bypass. And by the way, if the Aptera looks really aerodynamic, that's because it is. They say its air drag at 0.13 drag coefficient is less than that of the side mirrors or the windshield wipers of an F-150 pickup truck. Wow. Now, the same design principles apply to heavy vehicles. My team helped Walmart's fleet of heavy trucks, the world's biggest civilian fleet, to save half its fuel per case in a decade, including smarter logistics. But better technology alone can profitably make heavy trucks at least 3 times more efficient, as one maker expects to prove this year. And airplane efficiency, too, can rise 3 to 5-fold, like these decade-old designs by Boeing, NASA, and MIT. The Tesla's battery pack electric heavy truck due out this year more than triples efficiency with 40% sleeker aerodynamics, light weighting that offsets battery weight, and a 2-year payback. And this flight-tested air taxi revealed last August could fly nonstop from Dallas to Berlin with 1/6 a business jet's operating cost and 1/8 its fuel use even before electrification. A bigger version already designed could hold well over 20 seats and looks set to blow up aviation's business models. More leapfrogs are emerging. 2 years ago, MIT, University of California, and NASA tested this strong, tough 4.3 meter long structure that's 98.3% lighter than a typical aircraft wing. It's molded cellular engineering plastic lattices covered with a tough polymeric membrane. And every part of that shape passively morphs like a bird's wing to match the real-time flight conditions. Thousands of such identical cells, or if you want 10 or 100 times stronger alternatives, carbon fiber, carbon nanotube, can be robotically assembled into an airplane of any desired shape, opening revolutionary prospects for lightweighting, aerodynamics, and lower cost. So this has been prototyped as a car for Toyota, as an airplane for Airbus. It could make a vacuum balloon needing no helium, crush-proof, but buoyant enough in the atmosphere to lift 24 times the payload of a jumbo jet. Put that in a lattice airframe to help carry improved batteries, and solar-powered zero-emission electric planes might ultimately carry commercial payloads across oceans. So the oil and gas reserves, unsellable for competitive reasons, look bigger than the reserves unburnable for climate reasons. That is, oil owners are even more at risk from market competition than from climate regulation. The cost of getting automobiles completely off oil has fallen from $18 per saved barrel 10 years ago to under $7 today, heading below zero in the next few years. So oil became uncompetitive even at low prices before it became unavailable even at high prices. With electricity, as with fuels, technology and design are both moving efficiency into fast forward. Prior lighting improvements are being swept away as LEDs in each decade get 30 times more efficient, 20 times brighter, 10 times cheaper. What else changes this fast? The rest of the energy transformation, modern renewables. LEDs backwards are PVs, photovoltaics, and solar and in aqua wind power costs have plunged below the dashed lines. The cost of fossil fuels fed into US thermal power plants, often making old oil and gas and coal and nuclear plants uneconomic just to operate. The electricity revolution includes shifting from molecules and atoms to bits and packets, from hardware to software, from hierarchies to networks. Electricity is changing from centralized, supply-focused, fossil and uranium-fueled and brittle to distributed, customer-focused, renewable, and resilient. Or as some Canadian colleagues said last week, the 4Ds are coming at us: decarbonized, decentralized, digitized, and democratized. And the information age is informing, enabling, and organizing customers to take power into their own hands. You know, it's smart to sell customers what they want before someone else does. And customers are figuring out that they can buy fewer electrons, use them more productively and timely, produce their own, and even trade them with each other. For example, Dutch customers can buy renewable electricity directly from other customers on this peer-to-peer website of Van de Bron, literally from the source. My friend bought his electricity from the guy in the upper left photo because the price was right, and it's a really cute piglet. And then he got a long handwritten Christmas card from his electricity supplier. What big utility can dream of such customer intimacy? Indeed, powerful disruptors are converging on the electricity industry from at least 8 directions. And these 8 Pac-Men of the apocalypse move fast. They don't just add, they exponentiate. They're not lone wolves. They hunt in packs. They multiply quickly. They can gobble up half of utility revenue in this decade. And together, they're creating an alien competitive landscape faster than most utility cultures can cope. 7 years ago, all central power plants were called dinosaurs. And the full quote was, "Too big, too inflexible, not even relevant for backup power in the long run." Who said that? It wasn't Greenpeace. It was Union Bank of Switzerland. And now a new wave of Pac-Men is coming over the hill. Renewables in 2020 were about 90% of the world's total net additions of generating capacity. And International Energy Agency predicts about 95% through 2025 because, says Bloomberg, last year renewables became the cheapest bulk power source in 90% of the world, soon in all. Now, US wholesale electricity prices in aqua now widely exceed the average contract prices of wind power in blue, solar power in orange. Those are temporarily subsidized, but less than the non-renewables. And in unsubsidized world markets, renewables at or below 30 bucks a megawatt hour, the diamonds, keep falling through $20. In Saudi Arabia, they just hit 10. Modern batteries included in the filled squares are already cheaper than gas peakers. And Bloomberg finds variable renewables plus backup, which can be renewable, non-renewable storage or demand side, are now the cheapest way to meet a steady load. So that dethrones the so-called baseload thermal plants. The Paris Agreement's 1.5 degree aspirational goal would require stopping 80% of the 2010 coal plants by 2030, closing one a day till 2040, and virtually all by 2050. But renewables' new market prices make this profitable without counting mitigation benefits. So this mid-2020 study examined 95% of the global fleet of coal-fired power plants and found that, especially in India and China, using efficiently structured financial instruments to close and replace all those coal plants now with modern renewables, including battery storage, would be cost neutral in 2 years and would save over $100 billion a year by 2025. The fair and essential outcome of a just transition for coal communities is financially manageable because the US has only about half as many coal miners as it has yoga instructors. Gas comes next. New and old combined cycle plants no longer have a business case, even with frack gas. And their market is collapsing because all of their outputs, energy, capacity, ramping and flexibility, and ancillary services, like voltage and frequency stability, can be provided faster, better, and cheaper by locally customized carbon-free clean energy portfolios, illustrated here for the West Coast, that combine demand side and renewable and storage assets. And this could strand over $100 billion of planned US gas plants and $500 billion of gas supplies to fuel them. Investors have taken note. Now, modern renewables also scale up in a fundamentally different way. Traditionally, we built these giant cathedral-like thermal power plants, each costing billions of dollars, taking many years to license and build. But now each year, similar investment can build a factory that produces each year thereafter enough solar cells to generate each year thereafter as much electricity as your cathedral will ultimately make. Notice the 15-fold difference by the time you get to year 10. And that's why solar output worldwide is scaling faster than cell phones. And yet we're still told that only coal, gas, and nuclear stations can keep the lights on because they're 24/7, while wind power and PVs are variable and thus supposedly unreliable. But variable doesn't mean unpredictable. Here's how accurately the French grid operator in a stormy winter month forecast a day ahead the actual output of the country's wind farms. But they wish they could forecast demand that accurately. And a decade later now, East Danish wind operators are bidding wind power into the day ahead hourly auctions, just like thermal capacity, because today's wind forecasting is so accurate that the operators are more confident they can deliver on their contract tomorrow than the grid operators are that when they push the button, their peaker will actually start. Indeed, we built the grid because no generator is 24/7. They all break. And when a giant plant fails, you lose 1 billion watts in milliseconds, often abruptly, often for weeks or months. And grids manage this intermittence by backing up failed plants with working plants. But in exactly the same way, and often at lower cost, grids can manage the forecastable variations of wind and solar power by backing up those variable renewables with a portfolio of other renewables, all forecasted, integrated, and diversified by type and by location. So for example, in the ERCOT power pool with no big hydro dams and only 1% interconnected to adjacent grids, a 2050 summer weeks expected load shape can get much smaller and less peaky with profitably efficient use. Then we can make, say, 86% of the annual electricity with wind and solar cells and 14% from dispatchable renewables. This 100% renewable supply can then match the load by putting the surplus electricity into two kinds of distributed storage that are worth buying anyway: ice storage, air conditioning, and smart charging of electric autos, then recovering that distributed storage when needed and filling the last gaps with unobtrusively flexible demand. Then you have 100% renewable supply every hour of the year with no bulk storage and with only about 5% left over to make hydrogen or ammonia to decarbonize heavy transport and process heat. So the economics should be excellent even at today's prices. Some grid operators do such choreography today to far exceed last year's 38% renewable fraction in Europe and about 31% in the world. Germany and Britain are half renewably powered. Denmark expects to be 86% renewable this year. Scotland, 100%, they almost made it last year. And already they and some other European countries out on the end of the grid with modest or no hydropower can meet about half to 3/4, and did so for a whole year recently, or more of their electricity needs from renewables. And yet they added no bulk storage, and they have superior reliability. For Denmark and Germany, about 20 or 25 times as good as ours. The ultra reliable former East German utility, 50 Hertz, was 60% wind and solar power 2 years ago. They're targeting 100% renewables, all reliably integrated by 2032. So as my colleague Clay Stranger says, the operators have learned to run these grids the way a conductor leads a symphony orchestra. No instrument plays all the time, but the ensemble continuously makes beautiful music. For normal grid balancing, we have not just one-way bulk storage in magenta, but about 9 carbon-free ways to make the grid flexible, reliable, and renewable. I've sketched them here in order of increasing costs. Your actual costs will vary, but bulk storage comes last, not first, so we needn't wait for a storage miracle, although some are emerging, and the market isn't waiting. Now I want to look more closely at the second box from the left, demand response, using electricity more timely. And again, I'll put this in an ERCOT context. We did an hourly simulation for ERCOT in summer 2050, systematically combining 8 kinds of demand response that add up to about 3 times more than previously assumed. They engage electric vehicles, home plug loads, residential, commercial, domestic hot water, plus heating and cooling controls. And together, these can conveniently cut in half the summer daily load range, save 1/4 of non-renewable capacity, make renewable energy 1/3 more valuable, and pay back in about 5 months. And of course, eliminate the duck curve or dead armadillo curve. Let me digress for a moment into the February blackouts that by latest estimates killed over 700 Texans in February. These graphs show the February state electricity supply in 2 different styles. The early and late February, you can see, had normal operation with wind in green and solar in yellow whenever available, displacing gas in light brown and coal in dark brown. But mid-month brought 4 days of blackouts, probably the costliest disaster ever to hit the state. And most analyses focus on the supply side, how 2 February storms strained and then shriveled the state's bountiful gas supply by freezing unwinterized infrastructure, while many electric generators also froze, and some of them cut off supply to the gas fields. Gas plant output fell 17 gigawatts, coal 4, nuclear 1, just missing 3 more, becalmed and frozen wind 13, and snow-covered solar 1. But the resulting 34 gigawatt coincident generating shortfall, 21 of it thermal, exposed technical, institutional, and governance flaws that mattered only because of a huge demand event seldom discussed. Namely, intense cold boosted normal loads by an estimated 35 gigawatts of electric heating load at peak. And that is nearly twice the maximum load that ERCOT shed. It's twice the lost gas-fired generation. It's more than the total shortfall in supply. And it's nearly half the 77 gigawatt or so total peak demand that if met would have been 2 gigawatts over the summer record. So it's these vast heating loads that came from an often inefficient building stock, half housing, heated mainly by electricity in extreme weather. And that fragile combination risks hypothermia or heat stroke and endangers electricity and gas supplies. Where's this come from? Well, 2/3 of Texas homes were built before there was a state building code. Half have big air leaks and little or no wall insulation, limited attic insulation, single glazing. The blackouts could have been abated, if not averted, by asking Texans the day before to turn thermostats and water heaters down and appliances off, drain their pipes into containers, leave those out to freeze, and then put them back into unplugged refrigerators and freezers to preserve food. But customers were only asked late, vaguely, ineffectually to conserve energy, so they didn't know how to help, nor that they held so much power in their hands. Despite days of advance notice from weather forecasters and gas markets, supply and summer-focused state institutions were unprepared to sustain the interlocked supplies of electricity and gas, or to tell retail customers how to mobilize a decisive behavioral rapid response. Instead, leaders blamed each other, scapegoated renewables, and ended up not fixing a lot of important stuff. Now, a quick note about that 35 gigawatt peak electric heating load. I found the weather sensitive load in an ERCOT slide from the previous such event, and I simply scaled it according to how much colder it was. And in the residential sector, I accounted for the growth in population, which wasn't very much. Without that gigantic electric heating load, the supply failures wouldn't have mattered. I pointed all this out in Dallas Morning News op-ed on 14 February. Now, how did the much maligned renewables perform? So let's take a look at the renewable data. That's where I got those numbers. Uncontrolled grid collapse could have caused major equipment damage persisting for months or more, with just incalculable social and economic costs to Texas, the nation, even to global markets. And the calamity was averted by a few minutes at the cost of vast suffering and death. Unserved Texas electric demand, says IEA, 15-16 Feb, total over 500 times California's scorned load shed last summer. That doesn't count February's 15 gigawatts of load cuts in 9+ states of the adjacent SPP and MISO power pools, plus almost 5 million customers in northern Mexico. So wind and solar down at the bottom of the blue curve were initially blamed 128 times by Fox News in 2 days for triggering the Texas disaster. So is the Green New Deal, not yet adopted anywhere. But the aqua line shows how wind and solar power actually met ERCOT's dotted line across there, 2.1 gigawatt extreme winter peak expectation for all but about 10 hours. Constrained much more by expected actual low wind speeds than by freezing, but overperforming through the rest of the blackout week. And meanwhile, the red curve shows that operable thermal capacity had a much larger unpredicted failure. It fell from 70 to 45 gigawatts in a few hours. So renewables ended up actually underperforming the contingency expectations by at most 1.4 gigawatts for 1 hour, 18 hours into the outage, while over 30 gigawatts of thermal capacity was down. So that's over a 20-fold difference, which I guess the Wall Street Journal 5 editorials didn't quite understand. Of course, winterizing wind turbines would have been a smart investment to earn astronomical prices in the 80-hour crisis. And that would have added, though, only a few gigawatts when most needed, because as expected, winds were light, as they often are in February. And meanwhile, under 6 or 8 inches of snow, the shallow pitched Austin solar panels produced 60% less, 15, 16 Feb. And then they rebounded. ERCOT solar produced 2 or 3 gigawatts, 15 to 18 Feb, 4 or 5 the next week. Wind returned to a robust 12 to 20. So look who was most resilient. It was the renewables. I wish more of your state legislators understood this and were prepared to require weatherization in buildings and in gas infrastructure, not just electric. Now, meanwhile, as promised in my initial Ford and Edison slide, electric auto sales are soaring as battery costs plummet, and each trend drives the other. In the next few years, electric cars will cost no more to buy than gasoline cars, and good EVs are much nicer and cheaper to drive. These abundant cheap batteries imply distributed solar everywhere, gas industry distress, the end of thermal power plants, vast distributed storage and demand flexibility, and perhaps much of the grid's becoming a stranded asset like phone company copper. This prospect gives utility executives nightmares and venture capitalists sweet dreams. Ubiquitous electric vehicles mean an immense storage and ancillary service resource that's now parked 96% of the time. And you can already drive your charged up battery car to a soccer game in Amsterdam's Green Stadium, plug it in to help run the stadium, leaving yourself ample juice to get home with, and watch the game for free. The integrator, the Zurich-based mobility house, supplements those incoming cars with a bunch of Nissan Leaf stationary packs, 42% of them reincarnated in a second life, and all providing valuable services to the grid. In fact, the firm is building a 100 megawatt portfolio of stationary storage in Germany, Holland, and France. Here's the first 30 megawatts, all using packs that are in the EV business, but not in currently driving cars, like they're in inventory or recovered from crash cars. 3 years ago, this integrator installed the first electric car approved as a power plant on the German grid, able to get paid for providing frequency stabilization services. And of 21 services that stationary or mobile batteries can provide, the mobility house is already commercially active in 10 and launching 3 more. Efficient and electric autos are morphing from PIGs, that is, personal internal combustion gasoline steel dominated vehicles, to SEALs, shareable electric autonomous lightweight service vehicles. These 2 changes in technology and 3 in business model are all simultaneous, mutually reinforcing, vigorously in play, and sped by smart policies and strong commercial ambitions in both India and China. We're very active in both of those. Meanwhile, the rules are changing. In 2010, nearly half the world's new cars were sold in China, where only 5% of people owned one, and yet this 100-kilometer traffic jam took 12 days to unsnarl. Building roads causes traffic. Politicians are figuring this out and changing the rules to ensure that drivers get what they pay for, but pay for what they get. Non-automotive mobility is improving too. Bus rapid transit transformed this Hangzhou street on the left to the street on the right while carrying 800,000 riders a day. It can achieve subway route density at 5% the cost and now carries over 30 million commuters in nearly 200 cities. China also has over 200 million electric bicycles. Shenzhen has 100% electric buses and taxis, over 70,000 electric delivery vehicles, closing in on 100% of that market. And this city of 13 million people had more electric buses than the top 5 US urban bus systems had total buses. Chinese electric buses now drive about 30% of the world's bus kilometers. And urban design is changing too. China plans in the next 15 years to build new cities for as many people as America has. And so far it's designed cities around cars with an arterial vehicle network, but integrating and distributing where people live, work, shop, play, pray means people needn't travel far nor by car. Adopting a capillary web designed around feet means 2/3 less driving, 1/3 less concrete. It builds a human ecology with vibrant commerce, rich social life, equal or better throughput, cleaner air, happier people. And the 53 cities already doing this, more to come, will use little oil. So assembling all these opportunities, our 2011 business and design book, Reinventing Fire, rigorously showed how to triple the US energy efficiency and quintuple renewables by 2050, needing no oil, no coal, no nuclear energy, at least 1/3 less natural gas, while saving $5 trillion net present value, growing the economy 2.6-fold, strengthening national security, and cutting total fossil carbon emissions 82 to 86%, yet needing no new inventions, no acts of Congress, but with smart city and state policies led by business for profit. The first 9 years of this 40-year journey are pretty well on track, green actual versus blue proposed. I think largely because the private sector smells the $5 trillion on the table. And that's exactly what should be happening. These best buys are also the most effective solutions to big global problems that hazard every country's security and prosperity. And if you like any of Reinventing Fire's outcomes, you could support this transition without needing to like every outcome or agree which outcome is most important. Focusing on outcomes, not motives, can turn gridlock and conflict into a unifying solution to our common energy challenge. So stimulated by those US findings at the G20 5 years ago, China's National Development and Reform Commission published its roadmap for China's energy revolution, detailing how China can save over $3 trillion, run a 7-fold bigger economy in 2050 than 2010 using today's energy 7 times more productively, emit 42% less carbon, burn 80% less coal, and get 13 times more GDP from each unit of fossil carbon. This roadmap strongly informed the 13th 5-year plan, whose energy authors were our steering committee. And that strategy continues so firmly that China doubled its renewable installations last year alone, adding more wind power in 2020 than the whole world had added a year earlier. So if you extrapolate those on-track US adopted Chinese and similar European findings to the other half of the world, we could get to the minimal Paris Agreement ambition, a 2-degree climate target, about $18 trillion cheaper than business as usual. And reinvesting some of that in natural systems carbon removal could then get us to the aspirational and necessary 1.5 degrees, with trillions of dollars left over, and huge progress on the sustainable development goals. Making climate protection not costly but profitable should also simplify the politics. You know, the climate science models have conservatively understated the speed and the runaway potential of climate change. Climate policy models conservatively understated what we can do to stop climate change. Offsetting those two biases, what Jeremy Grantham calls the race of our lives, is very much on. Despair and complacency are equally unwarranted. And global CO2 emissions were actually flat in 3 of the 5 years, 2015 to 19, as energy savings and carbon-free supply growth averaged roughly the combined pace we must sustain for 2 degrees, or half the pace we need for 1.5 degrees. So now we must accelerate. And a powerful tool to do that, which I'll end with, is capital market dynamics. Incumbent energy suppliers feeling competitive threats understandably focus on the need for price to exceed cost. But many seem to forget the other part of the business condition, that value must exceed price. If competitors offer a superior value proposition and run off with your revenues, it doesn't matter if you can profitably sell what your customers are no longer buying. These energy transformations can flip markets with breathtaking speed. On Fifth Avenue in Manhattan in 1900, you have to look hard for the first car. Anybody see it? There it is. 13 years later, you have to look harder for the last horse. The horse and buggy industry thought it would have many decades to adapt, but Ford made the Model T 62% cheaper in 13 years. Car-owning households soared from 8 to about 60% in a decade, 3/4 financed by a GM and DuPont innovation called car loans. Well, today's solar modules just got 80% cheaper in 5 years, batteries 89% cheaper in 10 years. 3/4 of US rooftop solar is innovatively financed. Ford's and Edison's industries are merging to eat Rockefeller's industry. Thus, the pace of transformation is set not by incumbents, but by insurgents who are not inhibited by incumbents' business models, legacy assets, or cultures. Moreover, investors flee before customers do, because capital markets keenly sniff out disruption. And once they think you're in or even headed for the toaster, they don't wait for the toast to get done before they decapitalize you and invest in your successors. Already trillions of dollars have prudently fled the fossil fuel industry as it hemorrhages capital, talent, political influence. The world's top 16 listed hydrocarbon companies combined were recently worth less than Apple. Carbon Tracker investment analyst Kingsmill Bond explains carbon markets or capital markets brutal logic. He says any fast-growing challenger will rapidly take all the growth in a slow-growing market. As a rule of thumb, incumbent sales will peak when the challenger gets to around 3% market share, as in these examples. And that's because most investors seek growth, not mere size, and they try to excuse me, they try to sell just before sales peak, because then stagnation will strand assets and competition will drop prices. So that's why the coal industry has lost 3/4 of its market value globally, 99% in the US. But now this collapsing value is spreading to oil and coming next for gas. Peak nuclear power, peak coal use, peak auto sales, peak fossil fuel power have already happened. Fueled autos are now in their 4th year of shrinking sales because electric cars took more than all the growth. Last year, global plug-in auto sales soared 43%, while total auto sales fell 14%. The IEA says last year's pandemic slump undid energy's previous 4 years of growth, CO2's previous 9 years of growth, while renewables grew 45% faster, adding an extraordinary 278 gigawatts. So by the time demand recovers, if it does, renewables will probably have expanded enough to supply any future growth, tipping fossil fuels into permanent decline. And therefore, peak oil, peak fossil fuels, peak CO2 emissions probably all happened in 2019. Here's what that looks like. The bottom 3 wedges, coal in black, oil in red, gas in gray, stagnated before the pandemic. Last year, the pandemic's economic shock shriveled fossil fuels, while renewables, mainly wind in blue, solar in yellow, grabbed the capital. So total energy use may still rise a little, but wind and solar supply more than all the growth. So fossil fuels have turned from a growth engine into a sunset industry. And that news is speeding their delegitimization, their decapitalization, crushing their value in their cloud. In other words, investors are rapidly shifting their capital to both efficiency and renewables. Efficient use makes renewables gain market share faster. Efficiency outcompetes fossil fuels sooner. They reinforce each other. And in the past decade, world energy use grew only half as fast as in the previous decade. Further speeding energy savings could accelerate the self-reinforcing capital flight from incumbents to insurgents. Some of that speed may come from deeper, cheaper energy savings through integrative design, because its contagious, visually transmissible ideas might spread at the speed of YouTube and Twitter, perhaps rivaling even the speed of scaling solar power. One last thought. This global energy transformation isn't just fundamental, it's elemental. The first industrial revolution was the age of carbon, creating our prosperity and the world's mightiest industries from coal and oil and gas. But now that obsolete age of carbon is giving way to the modern age of silicon. Silicon microchips, telecommunications, software turn people from isolated to networked, systems from dumb to smart, grids from analog to digital, and potentially from digitized to democratized. Silicon power electronics make electricity interconvertible and precisely applicable, replacing fiery molecules with obedient electrons. And silicon solar cells enable the ascent of energy from mining the fires of hell to harvesting the breath and radiance of heaven. So our responsibility, our opportunity is to help enable the new energy system, not protect the old, to build back better, to move fast and fix things, so the global energy transformation can move at the pace and the cost of design and of software, not of infrastructure, and can be not constrained by the inertia of incumbents, but sped by the ambition of insurgents, like so many of you. Thank you all for your good work and your kind attention. Let's see if I said anything controversial.
Amory, how do you want to handle the questions? You want me to kind of, I've been watching the chat, so you want me to kind of read the questions separated from the comments?
Yep.
Yeah, I think that'll work great, Paul.
Okay. So that first one I think I see is you talked about the radiant cooling panels in Singapore, and someone asked, is there a local source, or even I guess a US source, for those radiant cooling panels?
No, this is all really new. They demonstrated that November 2019. Sorry, maybe it was January 2020, actually. They published it in September 2020. So make your own. It's pretty easy.
And somebody else had a good idea that you could, they're a big blank panel, you could put advertising on them to pay for them. And so they would be basically.
Yeah, it's insulated and white on the back, lots of white space to write stuff on. Of course, you just need, the 5 to 7C subambient. It's pretty easy to get that radiatively.
Okay, the next one was in your 27 watt solar home. The question is, are the appliances like the low wattage TV now cost effective or available, or is that still something being worked?
They're all on the market. This work was done by Amory Lovins, Phadke, and his team at Lawrence Berkeley National Lab. And they have a program called SEED, S-E-A-D, which is at superefficient.org, for getting the 20 or so major manufacturers of household appliances to make them super efficient. Of course, you can also make them low voltage DC, typically 24 or 48 volts, and do the direct DC microgrid. But yeah, nothing there had to be invented, and they keep improving further.
All right, next one may be a little out of the scope in light of the ransomware attacks on gas pipelines and such. Where do you see cybersecurity going? I don't know if that's applicable to today's topic, but if you have any thoughts, elaborate.
Well, we definitely have to fix it. I happen to have written what is still the definitive unclassified work on domestic energy critical infrastructure vulnerability called Brittle Power Energy Strategy for National Security, which we did for the Pentagon in '81. However, it was before the internet, before the cyber threat. So it's just about physical threat, which is equally real. And the way Internet of Things is now propagating with very little attention to cybersecurity is quite worrisome. So at this point, I would air gap everything.
You may have answered this one with a later slide when you showed China and their electric buses, but the question, what's the most efficient type city or school bus? And I guess, so maybe to elaborate, if there are electric ones, is that very common in the US? Are there any electric school buses running in volume?
They are emerging, and in fact, my local co-op in Western Colorado expects to make $40 million a year for the school district, I believe, by price arbitrage using batteries financed by the co-op in the district's school bus fleet. So yeah, that's a good trick. And I'm not that impressed with school buses generally. You know, we put our most precious cargo in a not terribly safe vehicle, and some of them don't even have seatbelts.
Right.
So a lot of work to do on those, but you might look at the work of Proterra and its Canadian competitor, whose name I forget, on electric buses. They simply took out a lot of weight using, among other things, carbon fiber to offset the batteries, just like Tesla can do with the semi truck. And you're saving the diesel propulsion, which for a truck is 3 tons of powertrain and fuel. So it's not that hard to make the weight work out. The school bus has a very defined route and schedule, which makes it easy to schedule in to provide grid services a lot of the time when it's parked.
Yep. Question, do you have much experience with power over Ethernet, delivered power over Ethernet? I guess that's certainly a low voltage.
Yeah, I don't myself, but there's a firm, well, there are several firms that do excellent commercial lighting that way, particularly one called Lumen Cache, CACHE, and they have a little module that plugs into a board for each chunk of lighting you want, and they're all controllable with a phone or a simple remote in a very sophisticated way, and they're all power over Ethernet. So you're saving a whole bunch of wires and controls, and that's now being produced in China and sold all over.
Okay, here's a good one. Do you see any completely new green energy sources coming? Anything beyond what's on the charts right now?
Well, my favorite one's burning energy studies, obsolete ones. We have a whole bunch of those. Yeah, they're, you know, as a physicist, I have no problem thinking that the physics we know may be a subset of a larger physics, you know, a superset that doesn't invalidate anything we know but adds to it. Gee, maybe that's how UFOs get around. Yeah, looking at the latest Pentagon report, there are some very nice breakthroughs coming at us in solar photochemistry and synthesizing CO2 into fuels at room temperature, not under severe conditions. So ways to build long chain molecules without Fischer-Tropsch. So I guess that's a new source. There are a lot of things that have been around for a while but may happen. For example, I used to work with with an innovator, you know, both of us working for Edwin Land at Polaroid, and he had the idea decades ago of optical dimension antennas, which could couple directly from sunlight to electricity if you put in optical frequency diodes. And at the time, nobody had lithography that fine, but of course now every chip maker does. You just need to make the optical frequency diodes, and apparently people have figured out how to do that. I didn't think it violated any laws of physics, we just didn't know how, but now it's starting to become practical. Those sorts of collectors could in principle be 80, maybe even approaching 90% efficient if you detune them the right amount to handle the solar spectrum. So that's a possibility. Somebody may, for all I know, come up with some kind of benchtop fusion. I've seen some stuff like that work. There's certainly something going on in low energy nuclear reactions, maybe muon catalyzed. We don't know what the hell it is. Some Some do emit neutrons and have fusion product you can measure. Dozens of labs have reproduced this. I don't think it has much economic future if it has a steam cycle, because even if the steam were free, the rest of the power plant would be uncompetitive with modern wind and PV by a factor 2 to 6, let alone with efficiency. But maybe there's a way to do it with direct coupling to electricity. So I wouldn't exclude that, although I'm not really expecting it. We don't need any of that stuff. In other words, we have plenty of technology now to do what we need to do and make money at it, but it'll get better. And that's why a lot more R&D would be good.
Yeah, I guess along that line, we haven't even begun to mine all the efficiency gains we have out there. So I think efficiency mining is probably.
No, remember 10 years ago, you could quadruple electric efficiency at 1/10 the price we now pay for electricity. So we didn't buy nearly enough of it.
Yeah.
And now we can do better than that. Now we're a lot better at integrative design too. It's not just better technology. So that's a whole lot of efficiency to go mine.
Yeah. So next question is really down to earth again. What about gas-powered lawn equipment, 2-cycle gas motors, pollution bombs, and they seem to be everywhere.
Those should all be electric.
Yeah, they should. And you could also convert your lawn to food growth and native lawns, and then quit mowing them would be the root source, I guess.
Air escape and or get a goat.
I'll get a goat, yeah. All right, let's see. Is there an example of affordable, highly efficient homes? There's a great need for that, affordable homes in Dallas, as there are certainly everywhere in the world, I guess.
Yeah, I'm trying to think of one near you, and you'd have to ask local practitioners, but there are quite a few people around the country doing affordable housing that is net zero or net positive, because after all, a lot of low income people are, even if you got them into an affordable to buy house or lease, would still be unable to pay high utilities if it's inefficient. So those things have to be combined. And the retrofit I showed, the Dutch Energy Sprong, is quite a good template for how to retrofit a lot of existing housing, especially social housing, to net zero or better.
All right, questions are coming in faster than I can ask them here, but we're still going down the list. How disruptive will blockchain be in distributed energy systems and for utilities?
Very, and RMI actually has an enterprise in that space called Energy Web Foundation. It's a Swiss foundation that writes open source software to go in the blockchain world, and it's already both field testing and in the wild with many of the 200 odd corporate members. And that's on the Ethereum platform, which has figured out now how to switch from proof of work to proof of stake, which cuts energy use 4 or 5 or more orders of magnitude, makes it much faster. So I think we're going to get out of the Bitcoin foolishness.
Okay, view on hydrogen for storage or transport, or?
Well, you can go back on rmi.org to my 2003 industry standard white paper for a long time called 20 Hydrogen Myths, MYTHS, which is still useful reading. Some things have changed, not a whole lot. I think now the business case is much weaker than it was for hydrogen in heavy trucks. It's still a good case for transoceanic airplanes. That would be liquid hydrogen cryoplanes. You have to design the plane because hydrogen is bulkier, but it's very light. And if you make the plane at the same time much more efficient, actually you can do 5 to 7-fold more efficient with liquid hydrogen, reoptimizing the engines using fuel cells, then it does get quite interesting. That will take probably a few decades, but I think we ought to speed up all the aviation innovation dramatically with a golden carrot that is a strong customer consortium that says to the industry, if you bring us a plane with, 4X, whatever, efficiency meeting all requirements, maybe in a couple of size classes, we will collectively commit to buy X copies a year for Y years at price Z. Go for it. We just took away your market risk. And this will, of course, change everybody's risk appetite, bring the best innovators out of the woodwork, because you're unbundling buying planes from buying the innovation that goes into planes. And this will get us out of the mess we're in now, where we're only making planes 1 or 2% a year more efficient. That would take almost a human lifetime to adopt the technologies we mastered 10 years ago. We don't have that much time, but I think we could transform aviation. And that's what Bill Otto is up to with that laminar flow bulbous looking plane I showed you, yep, which I visited last week, and it's quite remarkable. Once you do that, hydrogen or electrification becomes a lot easier. They'll get to compete. So I think electric planes will take short hauls, compete with biofuel and hydrogen, and probably win in a lot of medium hauls. Hydrogen probably still wins on long haul, but not necessarily forever. Electric may get there. And where hydrogen will really shine is in process heat for stuff like steel making. We'll make it electrolytically. We can make it at any scale because we're already wired to move the electricity around. And we'll make it largely in what is normally thought of as surplus or overcapacity, so that solar and wind can deal with the worst conditions. But that means most of the time you have the extra capacity paid for reliability, and that's worth doing. And having practically zero operating cost, you can price it just below the fossil fuels it displaces, and it turns out to be enough to decarbonize the heavy transport and industrial heat sectors. I have a couple of papers coming out on all this, one within weeks from RMI on profitably decarbonizing heavy transport and industrial heat, and then a companion paper August, September in MIT Sloan Management Review on the new business models and strategies that go with that.
And there's a related comment about mixing natural gas with hydrogen so that over time you're not ending up with a multi-trillion-dollar stranded asset of natural gas pipelines that maybe they could convert to hydrogen. So a mixture, I guess, is there.
You can do that if the metallurgy allows, or if you do a composite liner. So it's not a completely crazy idea. The Hythane and other schemes in Europe are looking particularly at this. However, I think in general, the centralized production and transport of hydrogen is probably not going to make as much sense as decentralized production in most cases. Of course, we'll have the big steam methane reformers stranded at refineries and able to make a lot of hydrogen if we decarbonize them. And those could go into pipelines if you retrofit safely.
Okay.
But electrolytic makes a lot more sense. And remember, electrolyzers are about to get very cheap. We'll get them at the China price like sneakers. And they can run flexibly. If they're cheap, you don't much care whether they run all the time. So they can be opportunistic and run when power is cheap or even negative price on occasion. And they can, the rest of the time, dispatch demand response back to the grid and get paid for that too.
Okay, why are geothermal ground source heat pumps not included in any of the analysis as an energy efficiency improvement for buildings?
Oh, I didn't get into a lot of good technologies, and that's one of them. And Paul, I know you used it successfully getting through the blackouts. Yep. It kept you nice and cozy using very little electricity, which you made from solar. But still, the field is not cheap, and although it's an excellent technology, it's probably not as cheap as super insulating your house so it doesn't need heat. You're going to need a water heater anyway, and actually you'll get more hot water per square meter of roof area from that super efficient electric heat pump I showed and photovoltaics than you would from even a thermal collector. And then you just put in a diverter valve and a baseboard radiator or a radiant slab coil to do a little hydronic heating on the few coldest nights of the year. And why have a heating system? If your house is efficient, you won't need one. If I grow bananas with that one down to minus 47F, you can probably do okay in Texas.
Yeah, and I'll mention, Dan posted in the chat, but this is recorded and your slides will be on the North Texas Renewable Energy Group website. There's a archive section for past presentations. And if anyone's interested, I did a ground source heat pump one about a year ago that it's archived up there. So if you're looking for more ground source heat pump, I did a whole hour on it. So let's see.
I spotted 8 typos as I went through my talk, and I'll send you a corrected version to post.
That just makes them human, right? What do you think about, let's see, developing countries that have large, not much electric distribution? Should they go in a distributed renewables or the centralized old model, or centralized renewables or a combination? What about developing countries? What's their best path forward?
Well, probably a combination, but they're all different and they'll all have distinctive needs in distinctive places. One of the things I should have mentioned, meant to put the slide in on this, RMI has had a program called SHINE till a year or two ago, run by Dr. Joseph Goodman. And we did 3 rounds of charrettes with industry, figuring out in each case how to cut photovoltaic system cost roughly in half. So that was about a factor 8 by the time we got through. The first round was what made Sunshot possible. It focused on balance of system and showed how to save about half of that. And then we kept making it simpler and simpler. And the latest version, you factory fab slabs of a number of modules, which all slide onto a truck, roll on, roll off. And then that whole collection of modules places onto a simple rack, snaps into place. That makes the mechanical and electrical connection. And you end up with about 2 or 2.5 cents a kilowatt hour unsubsidized electricity. I understand some Texas co-ops have been seriously interested in that. I think some may have ordered it, and you can now start to get similar hardware in Australia. So coming soon, I hope, to a Muni or co-op near you, or a factory or whatever. And you see, it plugs directly into the distribution network. There's no transmission required. You just stick it on the edge of town.
So we're coming up on noon. Amory, have you got a few extra minutes to go over, or shall I pick the last couple of questions?
No, I can.
Okay, we'll just keep going until we all drop off here, I guess. So this is a broad one. Comment on social inequities. Well, you mentioned, who needs a low energy bill more than a low income family, but how do lower income folks get access to efficiency? Home ownership is in decline. There's a lot of renters. They just pass on. There's that whole, any thoughts on low income people and tapping into the efficiency and renewables?
Yeah, there's a lot of financial innovation going on in that area, and rightly so. One of the more important elements of that, I don't know whether Texas has authorized this, but 32 states have, is PACE bonds, property assessed clean energy bonds, which provide cheap voluntary private capital for new or retrofit efficiency and renewables in buildings and factories, also water efficiency. And the way it works is through the property tax assessment. It's the same way we've always financed stuff like sewers and sidewalks in much of the country. And it means the landlord can get, without coming up with any capital of her own, can do a deep retrofit of the building, share the savings with the tenants, and the bond is paid off over typically 10 or 20 years, but everybody's got a positive cash flow from day one.
Okay,
And
there's a
if
couple
it
questions.
do it in the commercial sector, then it passes through in the tax portion of the triple net lease. So you don't need to renegotiate the lease to solve the landlord-tenant split incentive problem. That's really pretty elegant.
So there's several efforts in Dallas going on right now. The city of Dallas did a climate action plan. The Dallas School District, there's a lot of members who are on this call who've been really working, trying to drive the Dallas School District to improve. The local community colleges have also got plans. So the question is, on the RMI website, a lot of the school information people have been seeing is from 2011. Is there any effort at RMI right now to update educational facility improvements?
I don't know. There are now 350 people at RMI, and I don't know a lot of them. And there's so much going on, I can't keep up with it. But I think if you, let's see, if you write to outreach@rmi.org, that would be a good question for them. And maybe it will encourage them, if they're not doing that, to go back and review it. Of course, there will now be a lot more focus on ventilation in schools. And Fran Koster has a lot of important work on that. Let me get you his email address as we talk.
All right.
What's your next one, Paul?
While you're grabbing that, a couple of nuclear ones, I'll combine them. What's Bill Gates' efforts toward a greener nuclear plant, which I assume is still fission? And then there's a question a few down about nuclear fusion. What's going on in that? Any hope for that breaking through?
Well, yeah, I think let me repeat that a bit. And if you go to eesi.org/nuclear, you'll find a recent set of briefs to Congress on toward an evidence-based nuclear energy policy, I think it's called. And then if you go over to speakers on the right and scroll down to me, you can see my 20-minute brief and slides on why nuclear makes climate change worse. It's very simple. It's too expensive and too slow, so it buys less carbon displacement per dollar and per year than if you bought efficiency renewables instead. Nuclear has no business case anywhere for new build, and hardly any to operate existing plants, because their operating cost is generally uncompetitive now. And therefore, if we go on the present federal course of bailing out the distressed nuclear plants, we're not abating carbon emissions nearly as fast as if we chose the best buys first. So I think that's a mistake. Let me say something particular about the so-called small modular reactors, although that's not what Mr. Gates is promoting at the moment. He's got a pretty big one. As a matter of physics, reactors don't scale down well. That's why we build them big. But the idea of small modular reactors is to factory produce them and ship a bunch of them to a site, clone them together into something bigger, and try to make up for their diseconomies of smaller scale by mass producing them. Well, starting where we are now, they'll initially cost at least twice as much a kilowatt hour as today's uncompetitive reactors, which in turn are, according to Lazard, 3 to 8 times costlier per kilowatt hour than modern renewables are, let alone efficiency. And those in turn will get another factor two cheaper by the time you could build enough small modular reactors to see if you liked them and wanted to build a bunch more. So multiply 2 times 3 to 8, or if you use the Bloomberg numbers, 3 to 15 times 2. And let's see, that's a factor 12 to 32 or more times out of the money. You can't get there with mass production. Or I'll describe it another way. Today's modern reactors, prohibitive capital cost is about 78 to 87% for non-nuclear components. Only the rest of it is the nuclear steam supply system. Therefore, if the nuclear part and the steam coming out of it were all free, you'd still be about 2 to 6-fold out of the money compared to modern renewables. So this is a technology, future technology as time has passed. It doesn't matter how big it is or how small it is or what technology or fuel cycle it uses. There aren't any miracles that change the fundamental economics, and it just needs an orderly terminal phase.
Next one, there's a couple about education and training. First is, what 3 core disciplines would need to collaborate to create a college level sustainability degree to speed the disruption? And actually SMU has a Masters of Sustainability program that's been going on for about a decade. And it's a lot more than 3 disciplines, but I know you guys have some stuff going at Stanford with Peter Rumsey and yourself, and college level.
Yeah, I'm teaching extreme energy efficiency at Stanford Engineering, and we're spreading that to other schools. And Stanford's about to form its first new school in 73 years on climate and sustainability, and I expect we may roll into that. I would also, so I think integrative design and energy and resource efficiency generally should be a very strong cross-cutting theme. I would add biomimicry as the other great design revolution. That's innovation inspired by nature and art invented by Janine Benyus, in whose house I am at this moment, up in Montana. And if you don't know her work, the book Biomimicry is still a great introduction. But if you go to, say, asknature.org, you can type in your design problem, like, I want to dissipate heat, show color, pump stuff, walk upside down on glass, glue stuff underwater, whatever my design problem is. And out pop the names of the 17 organisms that have figured out how to do that, the scientific literature on how they do it, and the industry contacts who are imitating how they do it. So there are 3.8 billion years of design experience out there to be harnessed, and it is incredibly exciting stuff. And I think I would also pay a good deal of attention to social science on how to make these obvious innovations we've been talking about today obvious and attractive to more people, and clear away some of the behavioral obstacles. There was, for example, an exciting paper in Nature a few months ago by Leidy Klotz, Klotz, on subtraction. It turns out there was and it was written up beautifully in The Economist magazine, there's a newly discovered human bias toward adding stuff, not subtracting stuff. And this helps explain why it's so hard for many of us to design things out instead of adding more gizmos.
So for non-college,
I think,
you can, if you can.
And of course, renewables all over the place, renewables for energy supply and all sorts of other supply, including farming and forestry and such that do not treat soil like dirt, but really are emulating natural ecosystems.
So for non-college folks, trade type jobs, people who are coming out of the collapsing coal industry, what type of trade jobs would be best suited for the transition?
These are generally smart, resourceful people, and there's some good stuff going on in Appalachia on retraining. And I think just everybody becoming a coder is more one size fits all than is appropriate. But first of all, cleaning up the mess after the coal mines, and for oil and gas workers, plugging the orphan wells and infrastructure is a very good and rather durable occupation. I'm afraid there's a whole lot of that to do, especially in the Permian. And so much of the emission there is from a small number of facilities. That those will very soon become transparent. RMI is among the groups putting together a data fusion and display platform for all the ground, air, and satellite-based remote sensing. So there will be no place for emitters to hide. We'll be able to see all the methane and know who owns it. And I think that pressure will become intense. A lot of good jobs in that. And actually, any of the oil and gas majors or major service companies could do a global roll-up of that abatement opportunity in the upstream industries, and they'd be heroes to everybody, including their shareholders.
I guess also certainly a lot of electricians, both AC knowledgeable and DC knowledgeable, pipe fitters who understand not
Absolutely.
elbows would be good.
Yeah, and in fact, I'm writing with your help, Paul, a initially Chinese, then everywhere else, user or how to do it guide on the Tao of pipes, or it's about how to untangle your pipe noodles. And it's a fictional dialogue between two Chinese factory engineers discovering together how to get rid of most of their friction and fluid handling. Absolutely, we got to get this into the training for plumbers, pipe fitters, sheet metal workers. There's huge advantage to be gained there. I'll give you an interesting little story. There's a guy in Central California, Central Valley, old plumbers union guy, who figured out how to save most of the friction and energy in pool pumping. And California has 1/10 of the pools and spas in the country. Bet you got a lot of them in Texas. And he can shoot a picture of the existing rig and convert it into a drawing of how to fix it. And it's all the same physics, Paul, that you pioneered at TI, that we all learned from Eng Lok Lee in Singapore. This can save a household $3,000 to $10,000 a year. And that's a good business for the pool guys.
A lot of inefficient swimming pool pump setups around here. I'm always stunned. I don't have a pool. I'm always stunned at how much energy people spend a month on.
Oh, it's incredible. And California requires variable speed pumps, but for a lot of the installers, it's too complicated to set up. So they just set it to max pumping all the time, so they won't get blamed and they're not paying the bill.
Right.
But it ends up using more than before.
Let's see. Next
Lord,
question
87 things in the chat. Good heavens.
Yeah, I know. We're gonna have to put a hard stop here in a minute because they're coming in faster than I can read them. One of them that's always a hard one. Consumer demand is for energy efficiency is low. It says in Texas, but that's probably most places. How do you turn that around with the architecture and construction industries? That's whoever solves that will be my hero, I guess.
Well, it's complicated. Like we had an interesting case with a curtain wall office building, pretty typical, couple of 100,000 feet in Chicago. So it's both hot and cold. And the window seals were failing. It happens after 20 years, you need to reskin the curtain wall. And we figured out if you replace not with like, but with super windows, letting in light without heat, deep day lighting, good lights, lighting control, plug loads, you could cut the peak cooling load by 3/4. And then you could replace the HVAC, which you needed to do something about for age and CFCs, with a system 4 times smaller, almost 4 times more efficient. And you'd save so much money on that it would more than pay for everything else. And you'd have about a -5 month payback. In other words, it costs less than the regular renovation you have to do anyway that saves nothing. Well, it's going to take us decades to retrofit our whole commercial building stock, houses as well. So let's prioritize them according to when these major building events will happen to coordinate with those. So you get the deep retrofit with bigger savings and vastly lower costs. And at retrofitdepot.org, you'll find portfolio management tools for doing that. Actually, there's 100,000 20-odd-year-old curtain wall buildings in the country that are ready for that deep retrofit package. Someone ought to make a business out of it. Maybe one of you.
All right. Well, we could keep going forever. I think we're gonna wrap the questions up. Michael, you want to jump back in and wrap us up here?
Yes, I will. And, Amory, thank you so much. I mean, you are just a baseball metaphor. You hit it out of the park. And thank you so much. I mean, you always enlighten us with something new and thought-provoking and get us asking questions. And thank you for your responses today. Again, this will be, it's all recorded, and your slide presentation will be available to our members. And we're an education group, and so we're just trying to spread the wealth and your innovation and contributions to sustainability and renewable. Just the thought process is amazing, and thank you so much for your contributions. I want to just let everyone know, thank you for joining us and participating today. The unanswered questions, I don't know if Amory will have the opportunity to respond to those, but we'll collect those and get them to him. And if he has the opportunity, we'll try to get those posted back on our site as well. And then I just want to encourage everyone, if you're not a member, please join us if you can. $20 a year, it brings you a lot, just like Amory today. And then we have a meeting every month, second Saturday, 10 o'clock to noon. And our next one is going to be by Gary Olp. He is a sustainable designer architect here based in Dallas. He actually did the Plano Environmental Center, and he's done a couple of other sustainable buildings, passive design buildings here in the Metroplex and in the country. And so we're carrying on from Amory a little bit. We're going to take a look just at buildings and passive design and how his house is a prime example. And if you can ever get up to Aspen, he does do tours. Do you still do tours, Amory?
Yeah, we could generally figure that out. And the orangutans don't get rowdy till after midnight, so that'll be
okay. Well, I won't impose on you any further then. So
Amory, I've had one question that's not been answered. This is Mellon in Dallas. Where's my start video? Hello. Is your house off grid or not?
Oh, it's on grid because we want to take coal off the grid, and we're about a 3-to-1 net exporter. And we designed it specifically to.
All right, because one of the people that's also watching has a Mike Renner. He's like Mr. Off Grid and Mr. DIY, and has a 100-foot wind turbine in his backyard.
No, we
but he stays on grid. He stays on grid. He just pays the minimum. But we don't have net metering. Okay, thank you very much. I just had to know that.
So again, everyone, our next meeting is July 10th. If you can join us, please do. And thank you again, Amory.
My pleasure. Thanks for having me.
Thank you.
Thank you.